Okay. Does anybody have any questions before we start? Okay, today I'd like to talk about signal swing. I'm going to talk a little bit about measurement and simulation of high gain circuits. I've got a section on here on laboratory support. I'm going to go through it very quickly. I'll tell you why in a bit. And then I'd like to start moving into high gain single stage amplifiers. A fairly aggressive agenda. Review from last time. We went back to our reference amplifier, or our basic structure that we get by having a quarter circuit and this counterpart circuit, and then the half circuit, and then the full circuit. And we saw that we could make a different connection on the biasing voltage on the counterpart circuit. And if we connected it around to the drains of the left quarter circuit, we saw that we created, under certain conditions, something like a current mirror. And we saw that we could typically double the voltage gain by making this connection. And we did that by trading off one output. We lose an output, but we got two big benefits. A doubling of the gain, a doubling of the gain bandwidth product, and what else? Twice the slew rate. What else?
You don't need
a combo feedback circuit. Got rid of the combo feedback circuit as well. So if you only need a single input output, it's something very useful to consider. We talked about the basic current mirror. We talked about more advanced current mirrors. We'll talk about these in a little bit more detail later. We made the comment there are a lot of current mirrors that have been published over the years in the journals, a lot of them in textbooks, a lot of them in the patent literature. In the patent literature alone, there's about 600 patents that have the term current mirror in the title. They're not all different current mirrors, but a lot of them are. We said probably a lot of current mirrors don't even get patented or published. Wow, some simple concept, and yet so many different approaches around. Then we talked about signal swing on this structure, the single-ended amplifier, and we saw that by looking at the conditions that are necessary to keep the transistors operating in the high gain region, it established constraints. Those constraints happen to be lines in the V in common V out plane, and we saw the region of operation was bounded by those three lines. So what we saw is that for large values of V in common, the output swing was very narrow. For large values of V in common, the output swing is very narrow. For small values of V in common, the swing is very big. And then we looked at what happens if we change the gain of that structure. We can change the gain of the structure by changing the excess biases. And we saw that as we make the gain bigger, the gain is bigger because the slope is steeper. We see the common mode input voltage drops down and the output signal swing goes up as well. So in high gain applications, we can get a large signal swing on that structure. We then asked the question, what kind of common mode input ranges do we need? And what kind of difference mode swings do we need? And we looked at four extreme cases: large common mode range and large common mode input range and large output swing, small input range and small output swing, and one large and the other small. And we observed that there were applications for all four types. And it's important to know where you're using your amplifier to know which one of these types of swing characteristics you want to strive for. If you're doing a catalog part, what do you usually strive for? The top left. You'd like a large common mode input range and a large output range. But when you're using an op-amp in a dedicated integrated application, there's far more op-amps that are designed for dedicated applications than there are for catalog parts. You typically will design your op-amp to meet the needs that you require. Why don't you just go ahead and get a wide range on your structure, even for integrated applications? Does it hurt? Yeah, you shake your head. Why does it hurt?
Maybe you amplify some noise you don't want.
Could amplify some noise that you don't want. The bigger issue probably is we're going to see it takes a degree of freedom, or a couple of degrees of freedom, to get this large input range and the large output range. Degrees of freedom in your design are valuable. So if you use up a degree of freedom for something you don't need, then you can't use it for some other characteristics. Does that make sense? So probably the bigger issue is to use up a degree of freedom that does not benefit you. Let's play the same game with this structure. Is this a reference op amp? Not quite. It's almost, but what's different here? Diode connection. So the reference op amp only has a single-input output. This one, but you could have taken the other output on the reference op amp. This one has a diode connection, so it has a factor of 2 increase in gain and a factor of 2 increase in gain bandwidth product and slew rate relative to the reference op amp. Now, I'm going to do it for this structure. You can easily do the same thing for the reference op amp, and you can do the same thing for any other op amps we look at. I won't go back and do this for the other structures. I'm trying to show you how to do it, but then if you need it, you can do this for other structures as well. So, to keep M1 in saturation, what do we have to do to keep it in saturation? VDS has to be bigger than VGS minus VT. Let's keep M2 in saturation, excuse me. So VDS is Vout minus VSS. Has to be bigger than VGS minus VT. V2 minus VSS minus VT. VSS cancel, and we're left with Vout has to be bigger than V in common minus VT. To keep M4 in saturation, VDS, magnitude of VDS, has to be less than VGS minus VT. Magnitude of VDS is Vout minus, well, let's write that equation down. Magnitude of VDS is going to be VDD minus Vout. Has to be bigger than the magnitude of VGS minus VT. And VGS is V gate minus VDD minus VTH. And it's the absolute value of this. Now, let's see, what do we have here? This quantity here is the excess bias voltage of transistor M4. So then I can say that V out, so this is the excess bias of M4. So I can say then that V out has to be less than VDD minus V excess bias 4. Oh, maybe I should call it the magnitude of V excess bias 4, because that quantity we subtract is the positive quantity. Okay. To keep M1 in saturation, VDS, this voltage minus VSS, has to be bigger than V in common minus VSS minus VTH. VSS has to cancel again, and we get this equation. And finally, to keep M5 in saturation, we have this equation. If you look at those 4 equations in the V in common V out plane, they're all what? They're all locuses. In the V in common V out plane, what are all these locuses here? V out equals greater than V in common minus VT2. That's the threshold voltage of the device. So in the V out V in common plane, if this is an equality, what would it be? If it was V out is equal to V in common minus VT2, this is the threshold voltage. In the V out V in common plane. What locus is this? Mr. Kimler, what is this?
So
Is it a hyperbola?
no,
No. Is it a square? No.
I mean it's a linear
Line.
Yeah,
It's linear, straight line, right? Okay. And in the V out, V in common plane, what is this?
that's a line.
It's a line. V in common doesn't appear. This one here, in the V out, V in common plane. Remember, this is fixed, this is fixed, this is fixed, this is fixed. So what is this? A line. In the V out common V in plane, a line. So there are 4 lines. Okay. That's why I use script L, line 1, line 2, line 3, and line 4. Yes?
If you can clarify again, what do you mean by V in common? Like, is that different from, say, V2 or the...
Yeah. Okay. So if you have an amplifier, op amp, the input voltage should be about the same, right? If it's a high gain amplifier, your differential input should be nearly 0. So the value of that input is some voltage between VSS and VDD. That value is V in common. Okay, so V in common is equal to V1 plus V2 over 2 at the Q point. And it's approximately equal to V1Q, it's approximately equal to V2Q, because they're about the same. Okay. So here's the V in common, V out plane. I want to plot those 4 locuses. Line 1 has a slope 1, and V out's above it. That means it's to the left of that line. Line 2 is a vertical line, a horizontal line, excuse me. It has to be below it. Locus 3 is a vertical line, and the inequality says it has to be the left of it. And line 4 is a horizontal line, is a vertical line, excuse me, and it says it has to be the right of it. So this defines the region of operation of that op amp. If you're not in that region, one of the transistors is going to drop out of saturation. Okay. So I've identified the regions of operation here. And we see that the combo mode input range is bounded away from VSS. This circuit won't operate down, you can't take your inputs down to VSS. This is not a rail-to-rail input op amp. The input can only go down to VXS bias 1 plus VXS bias 5 plus the threshold voltage above VSS. If the threshold voltage is 1 volt, and you choose your excess biases to be a half a volt apiece, then you can only get within 2 volts of the lower rail with your inputs. Okay. The op amps you worked with in 230 or in the lab this time, can you take your inputs clear down to VSS? No, you go down too low and it quits working. Can you take your inputs clear up to VDD? No, it quits working if you take them too high as well. Something like this happens on the inside.
You can with the LMC 660.
Some op amps are designed, we'll talk about our design op amps to go rail to rail, but this was not designed to go rail to rail. Some are designed to go to one rail and not the other rail. On the top side, we can get closer. VXS bias plus VT3 minus VT1. If VT1 and VT3 are the same in magnitude, we get within an excess bias of the upper rail. If our excess bias is 100 millivolts, we can get within 100 millivolts of the upper rail with this device. Make sense? So we can get more common mode input towards the upper end with the structure than we can with the lower end. That's because we have N-channel input stage. So are we with me? So here's the constraining equations. for keeping the amplifier in the saturation region. That's those 4 lines. That's those 4 lines. Signal swings are also important performance parameters. What we looked at so far is the gain bandwidth product, the bandwidth, the slew rate. Signal swings are also important, isn't it? Oh, quite coincidentally, those expressions for the signal swing happen to be in terms of what set of parameters we've been using. The what? What I call the practical parameters. They're not in terms of W over L's. They're not in terms of quiescent currents. They're in terms of the practical parameters that we've identified. VXS bias 1, VXS bias 3, VXS bias 4, and VXS bias 5. Is that interesting? Is that interesting? Or is it just a curiosity? I didn't work for it. They naturally come out in this form, right? So now let's look at the performance characteristics we have so far for this amplifier in terms of the practical parameter domain. Any comments? Any comments? Some nice, clean, simple expressions that are nearly decoupled. A lot of these constraints, or a lot of these equations we have to satisfy only involve one of the parameters in this domain. So we're kind of lucky. The signal swing parameter equations and the gain expressions, the GB expressions, and so forth are conveniently expressed in the same parameter set. Well, I went back and I wrote all those expressions in terms of the natural parameter domain, in terms of W over L's and the tail current. And there's those expressions. Any observations?
Prefer the previous one.
What?
Prefer the previous one.
So do I. So do I. Wow.
It's hard to gain insight.
Yeah.
What we can do.
So you ask the question, what does W1 over L1 do? Well, it appears the denominator of this common gain expression has a square root. And it appears in the numerator of this gain expression right here. And it appears in this gain bandwidth product expression. Where else does it appear? Well, that's enough. In the numerator some places, the denominator some places, and it's in the square root form. What a mess. And we can make similar comments about some of the other parameters too. Okay? So, I wrote this in red. We have complicated expressions for almost all the characters of interest in this op amp in terms of the natural design variables. I hope we're at the point where you see why I spent so much time emphasizing which parameter set you want to look at and how many degrees of freedom you have. Because if you don't give it some thought, what are you going to be working in? If you don't give it some thought, what domain are you going to be working in? The natural parameter domain, right? And then you're going to have to visualize what's going on by visualizing the interrelationship between those natural design parameters and all these performance characteristics. Okay? A couple of comments about measuring AV. Anything that's challenging to do in the laboratory is usually challenging to do in a simulation. And usually anything that's challenging in a simulation is challenging to do in the measure in the laboratory. Okay? Measuring AV is challenging. You saw that in the laboratory this past week. It's challenging because it's so large. It's going to be even harder when we go to high gain amplifiers. The offset voltage in an amplifier causes a problem on measuring the gain in the laboratory. We typically embed it in a feedback network to stabilize the operating point if we want to measure the gain. And that's what the technique that we are going to go back and do in the laboratory today. Some of you did it last time. If you do that, of course, when we apply feedback, we have to be sure we don't go unstable. So we still have to manage stability. We'll talk more about how to avoid that problem after we talk about compensation. If you're measuring the DC gain in the laboratory, it's based upon the ratio of a DC voltage at the output divided by the DC voltage at the differential input. But the offset voltage affects the DC voltage at the input and affects the DC voltage at the output as well. So when you're looking at just DC voltages, it's difficult to separate gain from offset effects. So if you want to measure the gain, oftentimes you want to have a time-varying input, and the time-varying input will not cause the offset effects to change, but it will occur the signal-dependent effects to change. So maybe you put a square wave in to your amplifier, for example, and that way you can separate changes in the input from DC values of the input, same as the output. Where's the pole of that amplifier at? Of a typical amplifier, the 741 we looked at in the laboratory. Where's that pole at? It's about where?
Is the pole usually at the unity gain frequency?
No. Nope. Where's
Aren't there more than one? There's a low frequency pole and a high.
all we've seen so far is the low frequency pole. It's where? Or less. Around 10 radians per second. So it's maybe around 1 or 2 hertz or less. That's a low frequency. In fact, if you try to listen to it in an audio application, you couldn't even hear it. It's way below the hearing range of the human ear. The dominant pole of the amplifier is in the hertz range. If you're going to measure the DC gain, you want to be sure you measure it at a frequency low enough that you're not seeing it roll off. So the problem I saw in the laboratory this past week when I was in there is people measured the gain of the amplifier. Not quite. People measured the gain of the amplifier, but they may have been doing it at 100 hertz or kilohertz. So if this gain is 80 dB, which would be 10,000, and you're a factor of 2 decades past the pole, instead of having a gain of 10,000, you might have a gain of 100 if you're 2 decades past the pole. And that's what some people were measuring in the laboratory. If you put a square wave in to be able to see the changes in the output, you want to be sure that that square wave is a low enough frequency that you're below the pole. About how much below the pole do you think you want to be?
An order of magnitude.
You'd like to be an order of magnitude below the pole. If the pole is around 1 hertz, you'd like that square wave to be somewhere around 0.1 hertz. Make sense? Okay. If you put a very high frequency in, you're going to measure this gain, not this gain.
So for instance, on the data sheet, when they usually advertise 100 dB, like for the LM324, they must. This is the gain before the first dominant pole.
Yep, that's right. That's the DC gain. That's the DC gain. So when you use an amplifier, you buy an op amp and it's got a gain of 80 dBs or 100 dBs or even more. You think, well, I got a really high gain op amp. I'm going to use an audio frequency range. Where are you using it? If you use it in audio frequency range, you're using it out here. What gain do you have left there where you're using it? This might be the audio frequency range you're interested in right here, right? This might be where your use is at. That op amp doesn't have anywhere near an infinite gain anymore. That gain might only be 100 or 1,000, or if you're at the upper end of the audio range, it might be well less than 100. So your assumption that it's an ideal op amp starts to fall off quite a bit, doesn't it?
So what can we as designers do to pull that dominant pole out farther? Or is this inherent? Is there?
That's hard. That's hard. Because the reason it's here, we're going to show this when we talk about compensation. We've got to be sure that it's low enough so when we apply feedback, the second pole is going to be out far enough that it's past the band edge of that feedback amplifier. So if you're looking at a unigain feedback configuration, that's the most stringent feedback requirement. You have to have the pole past the unigain frequency, maybe half a decade past that. So your second pole actually is out here someplace. We've neglected that.
That's so that your phase plot will drop to a stable.
That's correct. If you don't have this, you will either be unstable or you'll be underdamped. If it dropped here and beta was 1, it'll be unstable. If it drops about here and beta is equal to 1, it'll probably be underdamped.
Is it the rate of closure criteria?
Pardon?
Is that the rate of closure criteria?
The rate of closure on
With 1 over beta, or with beta curve in the AOL. I'll ask you later.
Let's do it offline. I'm not clear on the exact definition of that term. So, okay. So the question is, what do we do to push this out? We'd like to push this out in many applications. Well, to push this out, we're going to show that the ratio between this pole and this pole is fixed. And it's dependent upon the DC gain and beta. So if we want to push this one out, then we have to push this one out. If we want to push this one out, we have to make the amplifier operate at higher frequencies. And that's hard. Okay, so conceptually we know what to do. Just push that high frequency pole out. Question is, how do you push the high frequency pole out? We have parasitic capacitances that limit how fast our circuits operate. And they limit how far we can push it out. Okay, so real good question. So what do we do when we get in trouble with this gain not being high enough? If you want to build an amplifier with a gain of 100, and your op amp gain is only 100, your circuit's not going to work very good at all with feedback. So what we do if you want to build an amplifier with a gain of 100, you might build 2 amplifiers with a gain of 10. Both of those amplifiers have a better bandwidth. And you cascade those 2 amplifiers together to get your gain of 100. So we typically don't do what you suggested and try to make that pole of the op amp go out because we don't know how to do it. But we will look at a different system configuration where we'll cascade lower gain stages together to get our gain up. Make sense? Measurement of GB is also hard by going by definition. If you want to do the definition of use the definition of GB, you measure the gain, the bandwidth, and then take the product. Well, the DC gain is hard to measure. The 3 dB bandwidth is hard to measure. So the gain bandwidth product is hard to measure by definition. Okay? However, if you embed the op amp in a feedback configuration, we know the relationship between the open loop gain bandwidth product and the closed loop gain bandwidth product. So invariably what we do is we rely upon that relationship to measure the GB of the op amp. We measure the closed loop GB and we rely upon the relationship between the two. Measuring R out is challenging. How big is R out for the op amp?
This must be very small for a catalog op amp.
Yeah, they don't do that great of a job. So ideally it's 0. But output impedance of 100 ohms is not uncommon. But when you put it, but it's hard to measure open loop because you can't stabilize, you can't make that op amp sit still open loop because the gain's so large. So you typically have to measure an open loop, a closed loop, the output impedance. If you look at measuring the output impedance closed loop, we can relate the open loop output impedance to the closed loop output impedance. So we say, well, just measure the closed loop output impedance then, and then do a calculation to find out what the open loop output impedance is. That's easy to do. Does that make sense? So if you have a circuit that has a certain output impedance, an easy way to measure the output impedance is to put a load on here and measure an open circuit. So you have VOC, is this voltage here, and then Vx is equal to RL over RL plus R out times VOC. So if you know VOC and you know RL and you know Vx, you measure Vx, then you can solve this equation for R out, right? So this is the way we can find the output impedance of a closed loop configuration. Put a load on here. Put an input here and look at the output in 2 different cases and solve this equation to find out what the output impedance with feedback is. This gives us R out with feedback here. Put a load on here, change the load, monitor this voltage here, and we can solve for R out. Because there's an equivalent circle looking back in here that looks like this, right? Once we get R out with feedback, then we go down and write the equation that relates R out with feedback to R out of the op amp. But here's the problem. R out with feedback for an op amp is approximately equal to R out with feedback is approximately equal to R out of the op amp divided by 1 plus A beta. If beta is 1 and A is 100,000, then R out with feedback is about 100,000 times smaller than the output impedance of the op amp. If this is 100 ohms and this is 100,000, then R out with feedback might be around 1 milliohm. Okay? So all you gotta do is measure 1 milliohm.
That only with single pole amplifiers.
Almost all of our amplifiers are going to be dominantly single pole. We will compensate them so they look like single pole. We will see why we do that later.
So what if the load was reactive?
Pardon?
So if the load was reactive, then this wouldn't apply?
I didn't put a reactive load on.
Yeah.
Just wouldn't apply if I had a reactive load.
Right.
I get a different equation. And by the way, it won't overcome the problem. Okay, so is there a problem measuring 1 milliohm output impedance?
Yeah. Sensitivity. Okay. I mean, so much error is going to couple into that.
What about putting a 1 milliohm resistor on? Could I put a 1 milliohm resistor on and voltage drop a factor of 2?
Well, it becomes a problem with our instrument at some
What?
point. It becomes a problem with our measurement instrument at some point.
Well, if I had a 1 milliohm resistor, could I make a 1 milliohm resistor? Yeah, that wouldn't be too hard to do. I could get a 1 milliohm resistor if I wanted one very bad. So if I put a 1 milliohm resistor in, the output voltage should drop a factor of 2, right? So adjust this. Maybe I can have an adjustable resistor, and when this resistor here causes the voltage drop to factor 2 from what it was open loop, then this resistor would be the output impedance of this structure.
Right.
right? That's commonly used to measure output impedance. Put a resistor on, adjust the resistor until the voltage drops to a factor of 2, then whatever that resistor is, that's the output impedance. What's wrong with that approach? Yes?
Can't you exceed the amount of output current?
Yeah! This op-amp might only put out 20 milliamps of current. So you start putting that load on to drive the output voltage down, and all of a sudden your output current saturates. Okay. So if you put a load on, you might be able to see a very, very slight drop in the output voltage. But if you put very much load on, I out max will be what you're measuring, or the effects of I out max, not the effects of the output impedance. Okay, so R out is challenge to measure. Make sense? I didn't even ask you to measure R out. I had this title differently. Last time I taught this course, it was problems observed in the laboratory yesterday. So this was problems observed in the laboratory for your predecessors in this class the last time I taught the class. Now I'm sure that none of you had these problems, but I think they're issues as well. So let me just go through them briefly because I think they point out to issues that typically crop up when you're looking with op-amp measurements. Problem, could not see the gain. The signals were too small. Tried to look at the input signal, and if you actually get to low enough frequency and your output signal is 1 volt, and it gains 100,000, your input signal is going to be 10 microvolts. It may not be easy for you to see the 10 microvolt signal on your oscilloscope. Okay. Amplifier offset made it difficult to see the signal. Maybe amplifier offset caused something to saturate. Output was real noisy. If you try to amplify that real small signal, you still have a small signal. If you have a 10 microvolt signal and you amplify it a factor of 100, it's still a small signal. And there may be a lot of noise in your measurement environment. Sometimes we don't have the supplies bypassed with bypass capacitors. And you'll get a little bit of oscillation on VDD and VSS. And you maybe think your output signal is noisy, but it's not a noisy output signal. Your amplifier is oscillating because the supplies are not stiff. Gain did not agree with expected results. Biggest problem here is not operating at the right Q point. You have an offset voltage that saturates the op-amp. Maybe the amplifier was defective. Maybe the multimeter was using it incorrectly, or maybe you didn't have the right frequency. It's important to always use a scope to monitor signals because sometimes the signals I see people looking at with a multimeter are not what they thought they were looking at. If you use a buffer amplifier, you have to worry about what that gain is, that buffer amplifier. This is a common problem. Voltage on a probe board pin did not agree with the voltage on an op-amp pin. For those of you that have been around when I've come in and tried to troubleshoot a circuit, you may notice the first thing I typically do is go touch the pins of the op-amp with the scope probe. I touch VDD pin, VSS pin, the plus pin, the minus pin, and the output pin. These protoboards tend to be flaky once in a while. And you don't know how often I'll find a situation where the voltage that you're putting into that strip of 4 contacts is right, but that's not the voltage that's actually making it to the pin on the op-amp. Sparks, this really happened. Sparks fly when the scope was connected to the circuit. Why did I get a spark when I did that? Here, I'll show you. Spark comes again. The red banana jacks. Every once in a while you've got somebody that does a real nasty thing. We have those banana jacks in the laboratory. Has anybody ever went in the laboratory and had the red and the black turned around? Normally black is what? Ground, and red is positive. Have you ever been in there when the black is on the positive side and the red's on the other side? I've been in there many times when that's happened. somebody has screwed around with them, and so now you're putting 10 volts across ground or something, and you get a spark. I've heard this many times. Signal generator was defective because of a monstrous noise on the output. You know, that test equipment almost never goes bad. So when you see a piece of test equipment that goes bad, you may be the first person in the last 5 years to observe a piece of test equipment in our laboratory that's gone bad. But almost all the time, when I find a piece of test equipment that's bad, and sometimes I've thought it's been bad too, it's typically an operator's error. Okay, remember that equipment doesn't go bad very often. So one reason is monster noise in the output, the scope wasn't triggered correctly. And so you've got what appears to be noise running across your screen. Well, it's not noise, it's that you don't trigger the signal to see what the signal really looks like. Did not see the output waveform from the signal generator. Sometimes the horizontal, maybe you're setting it up to look at a 1 kilohertz signal, but your scope is sweeping with a time base of 1 microsecond. So it looks like you got something that's not related to what you put in. Well, you don't have the right time base set up. I'm sure you guys know where this button is. Does everybody know where this AutoFind button is at? Yeah. Who said no? Who said no?
That was a joke.
It was a joke. I wish we could buy equipment without AutoFind button.
It's the only button I use.
I know. That AutoFind button is not your friend. If you know where to look for a signal, if you're measuring something, you need to know where to look for that signal at. You need to know what voltage range, you need to know what time base range, right?
Yes.
If you know what you're looking for, you don't need the AutoFind button. You push the AutoFind button, and sometimes it'll be 3 orders of magnitude off on either the vertical scale or the horizontal scale on what you want. Okay? So, AutoFind button on a scope is not your friend. Signals on the scope were too noisy. That's a common problem when you're measuring small signals. Take a signal that's in the 10 millivolt range or 50 millivolt range, and it looks real noisy on the scope. It is noisy. We don't have that much resolution on the scope to measure those small signals. And the bandwidth of that scope, we want fast scopes. So it's got a real high bandwidth. If you have a real high bandwidth, you've got a lot of noise. There's a bandwidth limit that you can set on the scope. If you go in and set the bandwidth limit, almost everything we work in is going to be in the frequency range well below the bandwidth limit. So why not make your life easier, turn the bandwidth limit on the scope, and filter out the noise you don't want to see anyway. Noise coming from your measurement environment and from the scope. I won't go through this. I've had a lot of problems with common and ground not hooked up correctly. Let me talk briefly about offset voltage. Offset voltage is comprised of 2 parts, a systematic offset and a random offset. A systematic offset is what the designer intentionally leaves in as an offset voltage. Most designers that intentionally leave much offset voltage in are not going to be designers very long. Random offset voltage is what is a result of random mismatch of the components. And the only way to drive that down, unless you do some sort of offset compensation, is to put large area on your input devices. The output offset voltage, by definition, is a difference between, and this is a different definition most people use. The output offset voltage is the difference between the desired output and actual output when the differential input is 0. And V in common is the quiescent common mode input voltage. So all offsets are relative to a common mode input. They don't oftentimes specify it, but like on an op-amp, 741, if you have plus or minus 15 volt supplies, it's probably relative to 0 volts common mode inputs. So you put the common mode input in here, ground the inputs. If this output is not what you want it to be, the difference between what you want and what you get is the output offset. It's oftentimes assumed that you want 0 volts. Don't let somebody else tell you what you want. You need to decide what you want. We can define the output offset by the common mode by the gain of the amplifier, that refers it back to the input. And you can equivalently then represent that offset voltage as a DC voltage source in series with one of the input pins to the op amp. When you fabricate an op amp, you end up with an offset voltage. You can't tell the difference between the systematic offset and the random offset after the op amp's fabricated. When you're a designer, there's a systematic offset and a random offset. But once it's fabricated, you can't distinguish between those two. You just look at the overall offset voltage. It's expected that the systematic offset be small, and there's easy ways to make the systematic offset small. It's one of the least things you have to worry about during the design stage. You can go in and tweak your systematic offset clear at the end, and it won't affect hardly anything else in your design. It is not necessary to make the systematic offset 0, although this can be done and is often done by minor tweaks. The offset can also be set to 0 by using a degree of freedom in the design of the amplifier. But this is generally an unwise use of a degree of freedom, although some textbooks, including the Martin and John textbook, suggest doing that. I'll discuss that in a minute. Yes?
Is it, if we really cared about it as a designer and we can't distinguish between the two after, couldn't we exploit some form of an E-trim or a laser trim to try?
Yeah, that works. Those work great.
Right.
It's strictly a cost issue. Anytime you do a trim, unless an electronic trim is something that there is no circuit, there is no trim bits required, then it's probably acceptable to do it on chip. But otherwise, it gets really expensive. So here's the one I wanted to refer to. If you look at the quiescent output voltage here, by definition, let's assume that we wanted the quiescent output voltage to be 0. If we want this quiescent output voltage to be 0, you can do that by picking the excess bias of transistor M3 to force that quiescent voltage to be 0. That uses up a degree of freedom. On that design, if the quiescent offset voltage was +1 or -1 volt, it probably won't make much difference in most applications. So it's an easy way to use up a degree of freedom, but you have so few degrees of freedom around, it's usually not advisable to use up a degree of freedom to make the offset voltage equal to 0. If you want the systematic offset to be 0 in this structure, if it's necessary, you might be better off when you're all done to go in and tweak a dimension on M3 or M4 slightly to drive that offset voltage down. Don't use a degree of freedom up to do that. If you are doing simulations with high gain amplifiers, this is something you can't do in the laboratory. You can take an amplifier and sweep the voltage on one side of the amplifier with small steps until the output voltage goes to where you want it to be at. And then you can fix that DC voltage and go ahead and put your AC inputs in to calculate your AC gains. I think I've got a picture on that. No, I don't have a picture on that. So once you know what that offset voltage is, then you can put a DC voltage source in series, and now you can put your AC inputs in. And if you calculate the operating point of your amplifier, which is necessary for doing gain calculations or gain simulations, then it will bias things to the right operating point. Make sense? However, if you sweep the DC input, find out what the offset is, put that DC voltage source in, do a gain calculation, and then you make a change in the dimension of the device, you're going to have to resweep that input again because your offset voltage is going to change. So every time you make any change in your circuit, you're going to have to go reset that DC offset voltage. Make sense? Can't do this practically in the laboratory, but we can do this in simulations. Last comment. When you do an AC analysis, Can you see distortion in the laboratory by doing AC analysis? By sweeping an input, maybe put inputs at different voltages in and see what the distortion is. So are you with me?
Depends what kind of distortion you're looking for.
Nonlinear distortion. So generally, if you have an amplifier, the bigger your input signal is, the more nonlinear distortion is present. And so the way you measure the distortion is to put bigger and bigger signals in, and whatever your signal is, you look at the harmonics. Can you do an AC analysis, change the amplitude of the AC signal to determine what the distortion is? Well, the answer is no. The way SPICE works, the way Spectre works, is if you do an AC analysis, the first thing it does is finds the Q point. Once it finds the Q point, it develops a small signal linear circuit at that Q point. And then you can put in a great big signal. You can put a 20-volt signal in, and you'll get great big signals at the output. Do they represent the signal you really see at the output of your circuit? No. All they do is represent what the output would be if the circuit were completely linear and you put that big input in. Okay, so keep in mind, any sort of AC analysis is inherently a linear analysis. They've already linearized the circuit before they do the gain calculations of the frequency response. Does that make sense?
Yeah. Does Cadence have, so that's in Spectre, right? Does Cadence have another simulation tool in there that doesn't, or maybe like piecewises it out and generates a new simulation circuit for different, for that type of test?
You have to do it. You have to do a time domain input. You can't do an AC sweep. So you have to do a time domain input, and then you can calculate the spectral characteristics.
You can only do a post analysis then.
What?
You can only do a post analysis then. You have to take your
Yes.
transient data and put it somewhere else.
That's correct.
Gotcha.
Okay. Yes.
What is your stance on homework extension?
So I don't have any stance. Is there a reason I should? Is there? Are you making a request or
Yeah,
so what's your request?
if we could have it extended until Monday.
Any objections? Okay, so that's fine. So this will be due on Monday. Just a passing comment. Extending is fine in this case, but sometimes I do an extension, I start getting questions. It looks like people don't start until it's about due. And so if you're making a request to extend it because you choose not to start on it, that's not the right reason to make the request. Okay, it's due on Monday.
Dr. Gaga, it's really interesting. We talk a lot about how it's challenging for us. And it makes me think about a comment I heard about data sheets once that the things that aren't reported on a data sheet are more important than the things that might use them. If you look at the LM324 output is superb. So I just kind of find that correlation interesting between.
When you're in my list,
I have a slightly different view on that. When they put a data sheet out, they only are going to be successful